Now let's start with session 4. So at the beginning of the session, I would like to discuss a little bit different question here. It's perceiving objects by perceiving the properties of them. So I want to talk about this question because for human, when we try to perceive the physical world, we want to perceive the objects. In many cases, we don't only care about the identities of them or what kind of object is them. We care more about the objects. So like here, I'm posing these examples here, like when you try to pick up an avocado from the supermarket, of course, you want to make sure like you're reaching out to the avocado. But when you choose which one to pick, there are lots of more about those objects you care about, especially the properties, like what's the shape of the avocado, what's the weight of it, and what's the hardness of it for this special case, because we want to make sure the avocado is ripe, it's not too hard nor too soft. So that in this case, the hardness is a very important property to us. So another very typical examples for us is the perception of clothing. So this is very typical and happens to everyone in our daily life. So we all have lots of pieces of clothes, and we see lots of pieces of clothes when we go to the shelves to pick one. And those clothes are mostly the same, but they are also make some subtle differences according to the properties. And for us humans, those subtle differences are very important. It tells us about like what does this piece of clothes feels when you wear them, and what do they look like. And we always try. We have multiple ways to perceive them, like using vision and using touch. And we have lots of properties to care about, like the thickness, smoothness, fuzziness, softness, and whatever. So those all make a feeling for us about what this piece of cloth is like. And I also want to mention the clothes example is that because not only because this is a very typically seen cases in our daily life, but also it's kind of challenging because it's not the same as the rigid objects, because they are deformable. They have all kinds of configurations. They have infinite types of configurations. But as humans, we still have some constant perception upon them, regardless of the configurations or the places we touch them or the ways we interact with them. So we did some explorations about how to achieve similar perceptions of object properties with robots. So, for example, to explore the physical properties of clothes, we built a system like this. So we have a robot arm here with a parallel grippers and tactile sensor on one of the fingers. And up here, we use a RGBD camera to take a overall view of the workspace, especially about the clothes that is laid on the table in a natural state. So the way we do is that we firstly use the vision to get a general view of the clothes, and we figure out a place to touch, and then we ask the robot to go ahead and to lay on the clothes and close the gripper, so that in this something like a gripping process, we can collect some tactile data. Specifically here, we are using a vision-based tactile sensor called GelSight to collect the tactile data. And the sensor is special because it can provide very fine, detailed, high-resolution data about the contact information. For example, for this piece of broadcloth shirts, when we ask the gripper to grip on the clothes, we can collect a sequence of tactile data from GelSight like this. So the color here represents the shape information, like the surface normals, and we can use that to reconstruct a height map on the contact surface. So for example, when we ask the robot to contact this cloth, we can see that the contact is growing from a small contact area to a larger contact area. And on the contact surface, we can see all those fine textures of the cloth material, and also the overall shape of the cloth that includes the shape of those foldings and the overall round shape, because on the other side of gripper, we have a hemispherical shape on here to make sure the contact is large. And the shape here is also very informative about the overall properties. So as a comparison, we collect a data set of 153 different clothes from our daily lives and put them on the table as our robot to go ahead to grip on the clothes and collect lots of the tactile data. And from those examples of the tactile data, we find that there are lots of differences between them. And although subtle, but they are very much related to the physical properties of the cloth where we ask the robot to perceive. So for example, they all have their specific textures. Some of them are very fine, like the satin, and some of them have very coarse textures, like the knit material, like the wool material. And also the overall shapes are different, like some of them can make very deep contacts of this hemispherical shape, and some of them make very blurred contact of a large area, like the knit material, wool material, and leather. And also the shape of the foldings are pretty different. And we believe that all those subtle information are very informative about the properties we care about this piece of cloth. So to figure this out, we train a deep neural network to understand, to evaluate all those properties that is pre-labeled by human regarding to this piece of cloth from the tactile data. So on the other hand, another challenges in this project is that where could the robot go ahead to go and touch the cloth? So we use vision to figure it out, because compared to touch, which can get very only local information, vision is much better at providing some global information. It tells about what happens in a much larger field of view. So here we use vision to take a picture of the cloth. Especially we use the depth image, which is cleaner about only the shape of the cloth, and we decide that the ridges on the clothes are the best places for the robot to grip on So we ask the robots to figure out where are those wrinkles and where are those ranges, and figure out where are the best places to grasp. Of course, we found that not all the wrinkles are the good places to grasp. So again, we use another neural network to figure it out. So now we have two neural networks. Firstly, we have one working on the tactile data, so that it helps us to understand the related properties that describe this piece of cloth. And we have another neural network to work on the depth images to tell the robots where is a good point to grasp or where is not a good point to grasp. And after that, we connect them together. Like firstly, we use this to figure out where is a good point to grasp, and the robot go ahead and grasp among the objects, collect some tactile data, and then we figure out what's the related properties to describe this piece of cloth. So sometimes we figure out, like, we found that a confusing problem here is, what if the tactile data is bad? So this might be because multiple reasons. For example, if the first neural network is not working properly, like the robot is not grasping at a good point, but at a very not a very nice point, so that the tactile data itself is very confusing, and it's not very easy to clearly perceive those properties from the tactile data. Or in some other cases, the secondary neural network is not working properly, so it's also very confusing about the properties. In this case, we just ask the robot to go ahead and do this exploration again. And the way we understand whether this data is good or bad is by measuring what's the confidence of the prediction of those property perception. So in other words, if we found that the network is predicting the thickness or smoothness with several properties, but that is kind of low. So it's more likely the data we get is kind of confusing, and we need to ask the robot to go back to grasp again and do another loop. So this turns out this closed loop perception turns out to be very helpful to get the robot have a better understanding of the of the properties. So here I'm showing an example of how this works. So the robot firstly go down to grasp on the object on this piece of cloth. So the place is actually nice, but here is a button, and that turns out to be very confusing to the robot. So the robot just go back and lay the cloth in another configuration and go back to grasp. And this time it's actually a bad position, so there's nothing in contact. And we figure that out from the tactile data immediately. And then we generate another grasp and collect some data. And this time the data is very clear for the neural network, and the robots can confidently predict the properties of the objects. And here we actually ask the robot to do a little task for the household, is to put the clothes into different baskets related to how to wash this piece of cloth, and the robot make the right choice. So we find that with this kind of closed loop retrial mechanisms, we can get a much higher accuracies on predicting the properties of the cloth. For example, if we look at the thickness, we make the chance of random guess as 0.2 because we ask human to put the thickness of the objects into 5 levels. So this turns into a classification problem. So if we ask the robot to do one grasp, one touch on some clothes that is not included in the training set at all, we can get it correct with a chance of 0.59. But if we ask the robot to do this closed loop perception, so we can get it correct with an accuracy of 0.65. So after we do this, we figure out there's another problem here. So the materials like clothes or fabrics is very complicated. And in the previous case, we selected the properties. We selected those properties to describe the clothes according to human perception. It's like we talk to human, like when you try to select a clothes or when you describe a clothes, what are the most important properties do you think that helps you? So we figure out there are several physical properties such as thickness, smoothness, fuzziness, and we may also use some semantic properties like which season shall we wear this clothes and what's the washing method of the clothes. But that is actually not enough in many cases. So this is a fuzzy process for human as well. We have some feeling of those objects. We have some feeling that something is helpful, something is useful, but it's very hard to clearly define those properties. So what happens in this case? So here we take a close look at the examples of fabrics, which is like clothes, but we kind of simplify the questions to the piece of materials. And we strip the fabrics from the post. And if we just have a picture like this as a human, but only look at those things, we have lots of description of those piece of material, like it's flexible, it's stretchy, it's thin, it's wavy or smoothing. Of course, there are also other ways, the other related properties that help us to map this piece of materials in our mind. And this is, we got this information from vision, from these pictures, but not only about these pictures. So we can imagine that if we drape this piece of cloth again, it will be a totally different pictures. It is a same piece of cloth. It gives us the same piece of same kind of feeling, but if we compare the two pictures, pixels by pixel, it's totally different. But we can still get the same kind of description of this cloth. And if we have if we can perfectly describe this kind of this property description of the cloth, and we can also imagine what it looks like. So it's the same with touch. So we can also explore the materials by touch. We can touch on different pieces, different places on the material. We can touch in different ways. We can get different data point every time, and those data give us the feeling of the cloth, give us the description of those clothes, this piece of cloth, and also, we can also imagine what it looks like if we have this description. So, and we can also connect the vision from touch because it's the same piece of material. But the always challenging part is what exactly is this piece, this kind of description? It's very hard to get a it's very hard to get a very clearly defined ground truth of those these representations. So if we think that probably a good way is to use unsupervised learning to find a description that can be shared between the two modalities of vision and touch. And hopefully that can help us to get a generalized and rich descriptions of those materials. So here we are dealing with two challenges. Firstly is how to describe these perceptions. And the second thing is that we want to make sure this description of the materials is generalized. That means it's invariant to the configurations and the sensor modality. Like either you're looking at the pictures or you're touching the fabrics, it gives you the same piece of description. And even though like you're touching on different places of the materials or you're draping the cloth in for different times, even by if you look at the pixels, it's totally different. But you should be able to find the same find the same piece of representation of this material because intrinsically it's the same piece of material and the property remains the same. And here to get the tactile data, again, we are using the gel size sensor. And we simplify the process like we lay this piece of cloth flat on the surface and made a simple fold in the middle and use a gel set to press on the folds on this piece on the fabrics so that we can collect some data like this. Like on one hand, we have the texture, fine details about the textures. And on the other hand, we can also capture the shapes of those foldings in the middles, which tells a lot about like what's the thickness of the cloth, what's the how easily can the cloth deforms. But of course, there are lots of other information which is hard to describe with language, but we know it's there. We know it's contained in the touch information. So to get this kind of descriptions, we train a network, a convolutional deep neural network, and generate a long vector from the tactile image. So we expect this long vector can make a good description of this material. So although it's for humans, it's very hard to define the long vectors. We don't know like whether this vector is related to the thickness or hardness or the other properties that are related, but we know these vectors describe the cloth. So of course, we can also do the same with visual data, both the color image or the depth image that describes the mostly about the overall shape of the cloth. So we feed them into different neural networks, and they also generate two other pieces of the vectors. And we expect all those vectors are descriptions of the material related to the property of them. And since the three of them are from the same material, we expect this description of the property shall be the same. So we train this neural network jointly and make sure as far as the data is from one piece of material, the descriptor vector shall be the same. And hopefully by this way, we expect to train a descriptor that will describe the invariant properties representation of the material. So to test how this works, so we can simply feed in different modality of data or even same modality of data and figure out what's the distances between the vectors that we got from different neural networks. So for example, we can got a piece of tactile data like this when we press on some materials, and this data can give us some intuition that it's something about like a knit material, so it might be a little bit thick, but it's very soft, fuzzy, and stretchy. And we also give a lot of candidate visual data here. And we feed in the tactile data into the tactile neural network, and we fed in the fed the visual data into the corresponding visual neural network, and all of them can generate some vectors that describe the properties of the materials. And we compare the distances between those vectors that we obtained from different inputs. And in this case, we find that the same piece of materials can generate the vectors that is closest to this tactile data. And even by looking at this visual pictures, we can figure out it represents some material that is kind of thin and soft and very deformable. But if we look at the other data here, like those two cases, there are some materials that looks very similar and has very similar properties. And the distances between those property descriptors are very similar. So that means our neural network is able to learn the descriptor that is exactly about only the property of those piece of objects. And for this, for example, this case, this kind of piece of material that generates the farthest distance between those feature vectors, and this one is has some properties very different from the request signals. So we can also we also compare the distances between the feature vectors across all the 19 fabrics which are in our test data set. So here we reorder those materials according to the similarities on the properties in human perception. So for example, these 4 of them, in human perception, we find that they are kind of similar, so we put them together. So we find that there's some confusion between them, but that exactly means that their properties are very close by. So, and if we compare the distance of their feature vectors, that they're also close. But if we look at the distances of those fabrics and the feature vectors of other fabrics, we find that is much further away. So similarly, for those 3 of them, they also share some similar properties, but different from the other ones. And for these 2, which are very close by, there are also some different fabrics than the others. Okay, so that is something I want to share today. So just to talk about some of our efforts on exploring how we can use tactile sensing or the combination of tactile sensing and vision input to get more understanding about the properties of the objects. Of course, this is there are still lots of things to explore in these directions, and I hope we can see more work in this field. So, and for our first session of this workshop, for the first session of this talk, this workshop, we will look more into the combination of vision and tactile sensing for manipulation. So we'll have 3 speakers here. The first speaker is Dr. Roberto Calandra from Facebook AI Research, and he will talk about in-hand manipulation using vision and touch. And the second speaker is Professor Peter Fox from University of Washington and Nvidia, and he will talk about to do some learning and modeling of touch sensing. And our last speaker is Professor Alberto Rodriguez from MIT, and he will talk about tactile-driven dexterities and use tactile sensing to do object localization and manipulation and assembly. Okay, so now let's welcome our first speaker, Dr. Roberto Calandra from Facebook AI. So Dr. Calandra has got his PhD from TU Darmstadt under the supervision of Professor Ian Peters and Professor Mark Dennismore, and he did a postdoc at UC Berkeley, and he has been working on the conjunctions of machine learning and robotics, and he did lots of works related to reinforcement learning and manipulation, and also the combination of tactile sensing and manipulation. So now let's welcome him.
Thank you, Wenzhen. gonna start sharing my screen. Please let me know if you can see. Can you hear me?
Yeah, works well.
Okay, perfect. Okay, good morning, everyone. On this side of the Atlantic was a fairly long night, so I'll try to keep it short and to the point. Today I'm going to talk about some of our recent work to trying to move towards in-hand manipulation from vision and touch. And just to give a brief motivation, I'm essentially going to start from the usual why is touch important. And touch sensing is a crucial sensor modality in humans, as it is the only sense that directly measures contact forces and thus interactions with the environment. And in a world dominated by Newton's law of motions, most motor control tasks are best represented and understood in terms of balancing of forces rather than joint positions. And as a humans, we all have experience of how extensively we use touch with sometimes barely realizing it. So if our glass is slipping from our fingers, we will automatically like grasp it. We use touch for measuring the mass of objects to distinguish between different materials, as we have seen just now, or even in the dark of, in our night to search for our phone without having a light on. And you already seen this video earlier today, but I'm going to play it again. The importance of touch is also fairly well understood for humans' motor control. And in these videos from Ronald Johansson at the University of Umeå, they essentially demonstrated how familiar motor control tasks, such as lighting a match, can suddenly become extremely challenging when we are deprived of our sense of touch. So in this case, it took several times longer to do it after losing the sense of touch. Now, also in robotics, it's fairly well understood, and of course, otherwise there wouldn't be this workshop, sort of thought that touch is a crucial sense that needs to be integrated before we can really deploy robots outside of structured industrial environment. For example, in houses or in our society, where we also have interactions with humans. And for example, some of our work we did several years ago, we had these two images, and we wanted to evaluate what is the stability of a grasp. And just from pure vision, these two images are virtually the same. It's almost impossible to distinguish which one is a successful grasp and which one is a failure. On the other hand, in the moment when we measure forces, it's very easy to disambiguate between the two, because on the left we will see that we have no contact forces, while in the right we can see that both fingers are applying some force to the object. So in my mind and in practice, integrating touch sensing in robotic manipulation platform have been proving very challenging for at least the last 20 years. And there are two main challenges that needs to be addressed before we can really deploy touch sensing at scale in the real world. The first challenge is the lack of good available tactile sensing hardware. And the second one is the difficulty of integrating touch into traditional analytical control schemes. In particular, in the moment when we start having very high dimensional tactile inputs with thousands or hundreds of thousands of covariates. So if we look at the literature in tactile sensing hardware, we all know that it's a gigantic literature. There are hundreds, thousands of papers, and here there are just shown some of the most recent ones. But what strikes as peculiar is the fact that most of these sensors are effectively prototypes that will never leave the labs. And if we look at actual commercially available sensors that can be built or bought, there are very, very few of them. ViTac is probably the most known exception, you can actually buy them commercially. They are mass manufactured, and that's very cool from a researcher perspective, because I can just go out there and buy one in theory. However, if we look at what are the important metrics for tactile sensors, there are several metrics that are really relevant. One of them is, of course, availability. Another one is cost, especially if we want to deploy these systems in the real world in that scale. We, of course, would like sensors to be as cheap as possible. Form factor is another important thing, because some of these sensors are bulky or are still relatively big, and instead we would like to have ideally sensors that are as small and as nimble as our fingers. Then there is what are the actual capabilities of the sensor. Some sensors provide single contact points, other sensors provide vector forces, other sensors provide topological maps, and effectively these capabilities might vary depending from which application we care about and which sensor we are going to use. And finally, reliability is a major point. As a humans, we can essentially go throughout our entire life with a single hardware, with a single finger, without never changing it. And in practice, for most tactile sensors that we have nowadays, they are fairly limited in terms of how many contacts we can make, how many objects we can grasp, how much force we can apply before they break or before they need to be recalibrated, and so on. So today, as a step toward enabling more researchers access to good touch sensing hardware, I'm going to present you Digit, the first mass-producible, low-cost, high-resolution, compact tactile sensor. Digit belongs to the family of vision-based tactile sensors and consists essentially of an elastomer, RGB LEDs, and a camera, where the formations of the elastomer are recorded by the camera as changes in color cues. These principles, which you've already seen in other sensors before, allows to generate rich high-resolution images of touch easily and without any moving part, with a sub-millimeter resolution and tunable sensitivity, depending from what type of elastomer you decide to use. Moreover, if the elastomer is equipped with markers, it also allows measuring shear forces, which seems to be an important information for many manipulation tasks. Now, what differentiates Digit compared to other sensors that have been published before is that Digit was designed from the ground to achieve three major goals. The first one was to have a form factor compact enough such that the sensor could be mounted on a multi-finger hand. The second goal was to have a high reliability to support large-scale data collection with hundreds of hours of interaction with the environment. And the third goal was to have a sensor which is easy to manufacture and to maintain. To achieve these goals, we developed Digit to be modular and also to use high-quality sensors with custom controllers and electronics and firmware. This enables the manufacture of the sensors through standard 3D printing tools and provide a path forward to scale up to mass manufacturing potentially. Compared to previous designs, Digit provides an easy-to-use platform with increased durability and serviceability overall. And in addition, our custom firmware allows for lightning control in full color RGB and enables frame rates up to 60 FPS. Just to give a brief comparison against what is probably the best tactile sensor, which is commercially available today, which is the ViTac. Both ViTac and Digit are compact sensors designed to be mounted on multi-finger hands, such as the Allegro from Wenzhen. However, while the ViTac provides 29 points of contacts, Digit has over 300,000 points of contacts. Moreover, while ViTac costs approximately $10,000, a digit can be manufactured for $15. Finally, part of the scope of this project was to lower the bar for doing research into touch sensing and really provide researcher a reliable platform for doing their own research on touch sensing. And for this reason, we open sourced the design of Digit, which you can find at digit.ml. And this includes mechanical files, include electronics, includes firmware, binaries of the firmware, and a Python interface. So looking a little bit more into some of the improvement that we did in this sensor, I want to start from the elastomer. In parallel to the sensor, we also developed a new process for manufacturing elastomers in a more reliable and simple way. And while our elastomers are slightly more transparent to external light, they are also order of magnitude more robust compared to other elastomers. Here there are images before and after 5 passes with a standard abrasion tool. And what we can see fairly clearly is that while the other elastomers have significant degradations in their surface, our has no visible degradation, which is of course great. In addition, our sensor is designed to be very modular, so that even if an elastomer breaks, it can be rapidly changed in less than a minute by removing that one single screw. And once you remove this screw, you can essentially replace the whole elastomer at once, very, very fast, with a sort of push and click mechanism. This also allows to in practice, tune the sensor to the desired applications. So for example, you might want to replace the gel, the elastomer with a harder or softer one, depending from how much sensitivity you require or how much force you plan to apply. Or you can also changing altogether the family of elastomer coating that you're using. So for example, here there are images taken from a digit using elastomer with different coatings. Starting from the left, there is a purely reflective coating for accurately measuring surface and texture. In the middle, there is a reflective coating with markers to compute optical flow. And on the right, there is a transparent elastomer with markers, which are barely visible, unfortunately, in this picture, to control finger position during grasping. A little bit similar to what finger vision does, if you're familiar with this other sensor. And in practice, this allows a lot of flexibility because you can have the equivalent of several sensors in one, depending on which elastomer you decide to mount. Now, after designing the sensor and manufacturing, we also decided to demonstrate its capability by tackling a fine manipulation task. And here on the right, you can see a Wonic Allegro hand provided with 4 tactile sensors, digit tactile sensors. And in practice, we know that characterizing and processing the rich high-dimensional measures generated by 4 digit sensors would traditionally be very challenging for traditional control scheme. So we decided to use more advanced machine learning techniques to integrate digit into the control loop of our hand. And in particular, we selected as an example of fine manipulation task, the manipulation of a marble between 2 fingers. Now, this is a very challenging task that for a robot require a significant amount of fine control of the contact forces, especially since the elastomer is not a rigid surface and is also a little bit curved, so it's actually really difficult to control this. And in our setup, in particular, we consider the control of 2 fingers, the thumb and the middle finger, for a total of 8 degrees of freedom for each finger. being controlled directly from raw tactile measurements collected by the 2 digits. And we started by setting up an autonomous self-supervised data collection pipeline where the hand would autonomously pick the marble and apply random actions to the fingers. And eventually the marble would slip down from the fingers of the robot and would fall into this red basket where it would settle after a few seconds in the middle. And at that point, we had a linear actuator that would push the marble back up, where the end would pick it up for the next episode. And sort of in this way, we could almost completely autonomously collect several hours of data collection for a total of 4,800 trajectories, trials. Now, unfortunately, you might have noticed that this is not a video of the final results and the final sensor that we published, but because of COVID, we didn't have access to the setup anymore after, essentially after publication, so we couldn't collect any nice video, unfortunately, and this will also show later. But in practice, for the as a model, we decided to perform how to control this task. We decided to use a model-based approach where we learn a forward dynamics model of how the marble will react to potential actions, and then we will integrate this into a model predictive control setting. So the dynamics model is learning in a 2-stage fashion from raw tactile inputs, where we first learn an autoencoder network with structural bottlenecks that essentially extract the XY position of the ball of the marble plus the amount of force that is being applied to the marble. And once we have this low dimensional feature space, we can now learn a dynamics model from this latent space that, given the features from the 2 fingers and the potential sequence of action for the 8 degrees of freedom, all the 8 degrees of freedoms, predict the next state. And once we learn this dynamics model and we train it, we can use it to predict the consequences of our action in the long term, and therefore we can control our robot using a model predictive control by continuously replanning what is the best sequence of actions to apply, and then applying the first one. The results also seems fairly convincing. So here we can see that our learned system significantly decreased the distance between the initial points and the final, the desired goal in tactile space, while if we compare to a PID controller, the PID controller is instead very, very difficult to tune because it's very high dimensional. And even after spending a significant amount of time trying to tune it, our learned system still outperformed the PID controller. Now, something that we also notice is that our system does lose marbles occasionally. So we have a failure rate of about 25% of marbles dropped, which is mostly due to the really difficult nature of the contact. So typically what would happen is that one of the fingers would just apply a little bit less force, and then it would lose the marble. It still outperformed PID controllers, but we also believe that collecting more data would essentially improve this and reduce it down with enough time and data. Unfortunately, I do not have any video to show you of the final policies on the hand because COVID impacted our lab operation while I was having vacations in Italy, so I couldn't take any final video. However, I can show you some manipulation sequence in the touch space, and here sort of the temporal sequences from the left to the right, where the green dots is the initial position of the finger, of the marble in the finger, and the red is the desired final position that we want to achieve. And we can typically see how as sort of time passes, indeed the position of the marble moves and becomes very close to the desired target position. So this was a gigantic, the overall project was a gigantic effort, and DIGIT would have not been possible without the contribution of an amazing and diverse team of people that did a lot of work, starting from the hardware design, the manufacturing process, the learning algorithm, and the experimental evaluation. So I want to thank them all. Now I'm almost out of time. I just wanted to point out that in parallel to DIGIT, there is another project that I care about, although I don't have time to talk about this here, which is another sensor called OmniTac, which designed at UC Berkeley. Now, the difference to DIGIT is that DIGIT was designed to be a sensor that can lower the entry bar to touch sensing research, while this OmniTac was more a way of developing a new prototype of high-end tactile sensor to test some new concepts of how to design this. And in particular, the goal was to develop a sensor more similar to a human thumb in terms of capabilities, such as being omnidirectional and being even more compact. The main novelty that I want you to carry home here, which is worth mentioning because it's different from GelSight or DIGIT, is that here we cast the elastomer directly onto the cameras, onto the 5 cameras of the sensor. And this really allows to shrink the form factor because we can shave off that 1 or 2 centimeters of empty space between the camera and the elastomer. And we can also remove the transparent support. And we also get nice images. We have a robot experiment. So you should have a look at this paper. So to summarize and to conclude, I think that touch is really a key sensing modality for interacting and sensing with the environment. And today I presented DIGIT, which is the first mass-producible, low-cost, high-resolution, compact tactile sensor. And we demonstrated his capabilities by learning a challenging marble in-hand manipulation task from raw tactile readings. And something that I think is very cool is that DIGIT is actually open source. So if you go to digit.ml, you will find all the mechanical files, electronics, binaries of the firmware, and a Python interface. Tomorrow, the paper will also be posted on arXiv. It's already posted on ICRA20, but on arXiv, it's going to be more accessible. And in the next days, we also plan to publish CAD files for 3D printing adapters for DIGIT for the most common parallel jaw grippers on the market. If you're interested in knowing more about DIGIT, please come to our poster on Wednesday. Unfortunately, we cannot give live demos as we originally planned to, but we'll still come up with something nice. And if you want to know more about OmniTac, please come to our poster on Monday. In future, we plan to use DIGIT for studying perception and control aspects of touch, and in particular, in-hand manipulation. And overall, the grand vision that I'm interested in studying and sort of nailing down is how to try to reach human-level performance in manipulation by using machine learning to integrate vision and touch. So thank you very much for your time.
Thanks, Roberto, for sharing. So the audience are very interested in the sensor. It's really a nice one. And especially people want to know, is that possible we can buy one for $15?
We do not produce at the moment or plan to sell DIGIT. We do open source it. So if you want, you can build your own, I guess.
So I guess everyone can use your CAD file and software design to make their own sensor?
Correct. All the information that we provide in the open sourcing allow anybody with access to a making space to build its own. In practice, you just need a 3D printer. You can order the electronics online from China or wherever you want. The only thing that is a little bit more subtle is the production of the elastomer, but we also have detailed instruction on how to do this.
Good. So what kind of interface does Digit provide?
So we wrote our own, essentially a Python interface so that you can access the sensor at fairly high speed. And the main interface that we provide at the moment is something like get image, where you get an image out of the sensor. But you can also set some configurations, such as how much light you want to have, what is the intensity of the light for the 3 RGB. You can set what is the frequency that you want, the resolution of the sensor. Oh yeah, the electrical interface is USB, correct? Is USB 2, although we use USB, USB 2B.
Good. So let's thank Roberto again for sharing. So let's move to our next speaker, Professor Dieter Fox from University of Washington and Nvidia. So Professor Fox has a research interest in robotics, artificial intelligence, and estimation. And today he's going to talk about his work on modeling and learning for touch. Welcome, Professor Fox.
Yeah, thanks a lot for inviting me over. It's very exciting. Let me share my screen, obviously. All right. See, I think this way I can see it. Can you see the slides?
It's the presenter view. Can you change to the
Oh, you can see.
View?
Yeah. Then here.
Okay, works now.
All right. I can't see the chat, but I think that should be fine. People should just interrupt me if they have any questions, I think. Yeah, hi everybody. Today I want to talk about some work we've been doing in the context of touch sensing for robot manipulation tasks. This is work that we've done at the Nvidia Research Lab in Seattle, together with various interns, as you will then also see. And we've been mostly working with the SynTouch, the ViTac sensors. And of course, I'm excited to see all these new developments, and just the sensor, that the Digit sensor looks like a really exciting development going on. I hope that some of the insights we got also translate, of course, to other sensors. So how I organized this was kind of by what kind of data we collect in order to maybe learn a sensor model or calibrate a certain sensor model. And the first very short section is about work where we're trying to learn something about touch sensors with kind of a minimal amount of supervision, where we're just collecting sensor traces and then apply a framework called self-supervised learning in order to learn kind of predictive models of touch sensing. And then the next step is, if you want to put a little bit more, let's say, modeling effort into the sensor collection process itself, then you can use, for example, tracking techniques to track the objects that the robot is interacting with. And maybe through these, you can then also extract a bit more higher level or more explicit model information about what's going on with the physical interactions between, for example, the sensor or the robot and the environment itself. And then on the third part, I want to talk about one effort that we started recently, which is on really going for kind of a fully calibrated setup where we went all out on the modeling side and saw how far we can get with this, and which on the longer run hopefully will also lend itself to learning or to designing very realistic simulation-based touch sensor simulations that you can also then use for controller learning. And then given time constraints, I think I started at, let's say, 7:58, so I assume I have a little bit longer than the 8:30 a.m. time, Seattle time, I must say. I'll briefly talk about where we are using vision only for manipulation, also just to put this kind of into context, and then I'll conclude at the end. But let me first briefly talk about how we can use pure sensor traces. First of all, again, the sensor we're using is a ViTac sensor. It's kind of this deformable fingertip that mostly consists of kind of a deformable elastomeric skin, this green skin that you can see on the left side here. And inside, this finger is then a conductive fluid. And the sensing itself happens at the core of that finger using 19 electrodes that provide impedance information. And this impedance changes depending on kind of how this fluid field inside the finger deforms based on interactions with objects. Here's just an example of what this data looks like, where especially in the middle section, the 19 electrodes are colored by the responses they are giving as the finger is interacting with surfaces. Now, the problem is that these electrodes, they do not provide directly, let's say, immediate force information, and they are also not necessarily very well localized with respect to where the finger itself is making contact with an object and what kind of shape the object has. So that kind of information has to be inferred through hopefully the learning processes or modeling processes. By the way, I hope that the videos get through reasonably well. If not, I might have to stop them once in a while. But this is work that Giovanni Sutanto did with us as an intern. We published this at ICRA last year. And again, in this first part, it's really about using minimal supervision in order to learn a sensor model that you can then use for control. And this is, of course, very much in line with the recent advances that you can see in deep learning, where various people, leading people in the field, in the community, like Jan LeCun, Jeff Hinton, also mentioned very clearly that self-supervised training is, of course, a very important direction for making deep learning techniques viable in the real world. So the idea here is that we have a robot platform, as you can see here on the right, and we have the fingertip just interacting with objects. And the only supervision is kind of the relative motion of the finger in the 3D space. And then we collect these 19-dimensional electrode measurements. And then based on that information, we want to learn a model for these electrodes. Let me first show you here the video on the right. So where again, the finger is moved to make certain kinds of contacts with surfaces. Okay, here's just a rotational motion. Here's the same now, see, showing in the internal kind of simulated model of the robot, but that is not explicitly actually used in the process. You can also do then, for example, a translational motion where the finger is moving forward and backward. And again, for this data set, what we collect is the relative motion of the finger as we're getting through the kinematics, through the joint sensors of the robot arm. And along with those, we collect measurements of these electrodes. And then you use deep learning techniques in order to learn a dynamics model that say, given electrode measurement at time t, given relative motion or control of the fingertip in the finger's frame of reference, you want to predict future electrode measurements. And rather than learning this mapping just from 19D to 19D, what Giovanni developed is a technique that first maps the raw measurements to a lower dimensional latent space, and also imposed additional structure on that latent space such that the changes in latent space are correlated with changes in the pose space of the finger, which means straight motion in the finger should hopefully relate to straight motion in that latent space between points in this embedding, okay? And once we have that, you can then do control using this embedded space where, for example, you put the finger on a surface and you give it as a goal, a measurement that the robot should sense, that the finger should sense as a target, and then the system knows what controls to apply in order to achieve a certain, let's say, measurement configuration. And this way of phrasing goals in the measurement space, in the sensing space, is pretty popular, especially in end-to-end deep learning. I must say it clearly also has limitations, because the question is always like, how do you really specify a goal in a general way? Because you cannot always predict the desired measurements. But anyway, this works reasonably well here then, where now you can see in this case where the robot, in this case, is given a goal measurement such that the part that you can see here, that red marked piece on the fingertip, should sense the contact. And based on this learned model, it now knows, the controller knows that it has to actually rotate the finger in order to achieve this desired target contact. Okay? Here you can see this again, but now highlighted the contact point as extracted from the sensor measurement, which is not used explicitly in this model here. Here's another one now for a sliding motion, for example, where the sensor knows, or the model learned, that it has to pull the finger back. So again, this is very intuitive in the sense of where you're placing the finger on a surface, imagine, and you're closing your eyes, and now you're trying to achieve a desired kind of contact with the surface. And this model that Giovanni learned here then was able to give you the controls, like how you need to rotate or slide or translate the finger in order to achieve this desired configuration. The nice thing about this framework, again, is that you can do so with just a minimum amount of supervision. The disadvantage at this point is that these kind of models are reasonably limited with their generality and to how many different tasks they can be applied. Okay, so now I want to go to some work that we've done where we try to provide in the data collection process some more supervision in order to learn models for the SynTouch sensor, the ViTac. So you can imagine here, for example, is a setting where we have an object, a box, and on the right-hand side here you can see the SynTouch, and we are interacting with these objects in the world by just pushing them around, right? And this is in the full 3D space. What we need in this setup is we need a 3D model of the objects, and once we have this, we can use a framework that we developed a while ago called DART. Tanner Schmidt developed that, where we use a depth camera to accurately track an object as it's moving in the space, and also track the robot, as you can see here, hopefully on the video on the right, where the gray points are the depth camera measurements, and you can see how we can track both the objects and the robot itself. Okay. So once we have that information, Bala Sundaralingam, he developed a technique that can use this information now, along with a dynamics model for the forces involved in order to push an object. So you can see here on the right, where we first use DART to track the objects, and then based on the fingertip position and the object position estimated over time, he's trying to determine at every time step the forces that were necessary to explain the motion of the object, okay? Taking into account both the linear motion and the angular, the rotational motion of the object, okay? So you can see here on the lower part, you'll now see a little animation showing a top view of that motion, okay? So here first the object is being pushed, and then down there, you can see the motion of the object, and alongside also he's estimating the 3D force vector that explains that motion using this physical interaction model. Okay, one limitation of this is that it is using DART, the tracking, as kind of a ground truth system. So also published at ICRA last year, Sasha Lambert developed a technique that uses factor graphs in order to come up with a more accurate modeling of the contact between the finger and the object. As you could see in the upper left part here, if you just use DART, the finger might not actually be in contact with the object itself. So there might be whatever, 2, 3, 4 millimeters offset. And again, he developed a technique that doesn't only estimate forces between the fingertip and the object, but also re-estimates the poses so that they are physically consistent with the context. You can see this now in the animation here on the right side. Okay, where you can see that the contact point between the fingertip and the object is always nicely on the surface, and thereby it can, of course, explain the kind of motion that we're observing much better. Okay, so this is just a way of refining those estimates by combining DART with this very explicit contact modeling and making it more consistent. So based on this kind of sensor data now, Bala then learned a sensor model that goes from electrode measurements to 3D force vector, 3D the magnitude of the force and the direction of the force. And once you have such an explicit model, you can incorporate it into a controller and start manipulating object. So on the left-hand side, for example, what he demonstrated is that you can pick up deformable objects. So this is a bottle that you can squeeze. And again, he's using in real time the forces extracted from the electrode measurements of these 3 fingertips. You can also determine when the object, for example, touches the surface again, so that you know when you have to release the object. On the right-hand side, you can see an even more subtle kind of placement operation, which is not so easy to put it on that surface so that it doesn't fall over. Okay. And again, this is the advantage of this kind of slightly more model-based approach, that once you have this force model for the sensors, you can actually incorporate them into standard kind of controllers for this setting. Here's another task where we now incorporated that more into a reactive system, where the overall approach does the following. So here we want to, for example, pick up this cup that you can see here on the left side. Okay, we're using an Allegro hand, again with the ViTacs on there, and it's mounted on a KUKA robot. And what the system does is the following. We first use a depth camera to detect the object using, I think in this case was still pose-CNN, but kind of a 6D object pose estimation framework for estimating where the cups are. So here are 2 cups, as you can see. Then based on the cup position, we can generate target poses for the fingertips where the Allegro fingertips should go. You can see these here on the right side, these little red dots. Those are target poses for the fingertips. Okay, so all of this is estimated in real time. These poses now are sent as goal points to RMPs, which are Riemannian motion policies, which is a reactive control regime that then reactively kind of controls the Allegro hand and the KUKA arm in order to achieve these goal points. Okay, and then once it's there, it's closing them in order to make contact with the object. And once it's making contact, we're using the tactile feedback that Bala was able to learn based on his data in order to control first how the cup is being held by the robot, and also when we want to place it to determine when the placement happened. Okay, so I'll show you just a video of how this now works. On the right-hand side, you can see the DART estimate along with the pose estimate, with the detection of these objects. Okay, and the robot now tries to put it back onto the other cup. But Carl is not nice and just keeps on teasing the robot, and we keep track of all of this in real time. And in this case, in this video, as you can see, actually the goal point is not defined with respect to the fingertips of the robot, but the goal point for the motion controller is actually defined with respect to the cup where it wants to place it. If you look here on the right side of this video, I hope you can see my mouse well, the goal point, this red dot, this is the goal point where the cup wants to move, which is defined relative to the target placement. Okay, and all of this is then fed into these Riemannian motion policies to generate the controls. So you can see here that the robot is then actually able to pretty gently place this object back down onto the other one. Okay, so this was now kind of going from almost unlabeled data to a more sophisticated, let's say, labeling effort where we're using visual tracking together with contact information in order to provide the supervised data that we need to learn the mapping from electrode measurements to forces actually being applied to the fingertip. Okay, but so far all of this, what it gave us was kind of the 3D force vector, but often these models don't even give you exact information about which point on the fingertip is in contact with the object. And what it clearly doesn't give you is any information about the actual deformation of the fingertip. So where we wanted to go in this next step is if we can learn a much more detailed model of the real physical interaction between the fingertip itself and the objects. Okay, and that gets us to kind of a much more stronger effort on the calibration side in order to collect this kind of data that we need for these more sophisticated models. Okay, so what we used was the following. We use an ABB Yumi robot, so they are very precise and repeatability on achieving certain points, configurations in the configuration space of the robot. In front of the robot, we placed what you can see here in the middle, where we took the biotech. Okay, we 3D printed, and this is work that was led by Yashar Narang, so who's a research scientist in the lab. And this is a paper that's going to be published at RSS this year. So what he did is we 3D printed this kind of array on which we can also then, with a 3D printed holding pin here, we can place the biotech sensor in a very accurate, precise position. This plate is also mounted on a 6D force torque sensor, so that we can measure in real time, of course, the forces being applied to the biotech. And in order now to calibrate that, that array or that measurement device here relative to the Yumi, what Yash did is he also printed these in the 3D printed process, designed these holes that go around that array here. He then printed a pin that you can then place into the Yumi's gripper or into the end effector part, so it's not actually held by the gripper. That wouldn't be precise enough. And then by inserting that pin into these holes, as you can see here on the right, and doing this for all of them, you can then estimate a very, very precise position of the biotech relative to the Yumi. So Yash found out that calibration error is then about 1 millimeter over all of the relative pose of the Yumi and now the biotech sensor. Then, if you look here on the right, for example, what we can do is you can now 3D print an indenter, like in this case, this black kind of 3D printed device. You can now start poking the biotech sensor. That poking will also be measured. You can get the biotech electrode measurements, but also you get the force torque measurements from the 6D force torque sensor. Okay, and because everything is 3D printed, we also have, of course, a full 3D shape model for everything that's going on. Okay, so if this is where Yash would have added and just collected that data, that would not have given you any, let's say, information about deformations or things that are really going on with the sensor. All that would have given you is information about electrode measurements and the 6D resulting force torques on the biotech, but nothing about deformations. So what Yash then did is, first of all, again, he developed different indenters, 9 different indenter types. And here in the middle, you can see one example for how this process then goes, where you can see in this video kind of the Yumi now poking that biotech sensor various times. So overall, we have more than 300 unique trajectories. So this data set will be made available to people. Okay, so you can use that. But the key thing is, again, we wanted also to know what is going on in the
Hello? Hello?
element. They agreed with that Yash now knows much more about the physics underneath the biotech than
Excuse
others.
me, Dieter. Your internet went out for a few seconds. Do you mind go back a few seconds?
Yeah, let me go back. Was it like on this slide? Are we good again?
No, previous one. So you're about to finish the previous slides. Yeah.
Oh, okay. But did you see the video?
I think not.
Oh, okay. So in the middle now, if you look in the middle, you can see now how the Yumi is kind of poking that sensor, and this is sped up here, of course, but how the Yumi is poking the biotech with these different indenters. Okay. Does it work? Did that now work?
Yeah, it works well now.
Okay, perfect. So he then generated, again, with these 9 different indenters, he did more than 300 different trajectories on how to poke the objects, how to poke the biotech with them. And that data set will be made available to the community, of course, right? So that you can use it for your research. But again, stopping at this does not yet provide you any information about what's really going on at the physical level with the biotech sensor itself or with deformation. So what he then developed, he used a tool called Anvil, which is a finite element modeling tool, and developed a very fine-grained finite element model of the SynTouch. You can see here on the left. So he modeled that there is a fluid inside. He modeled that you have a deformable surface skin. He had a 3D model of the interior core of the sensor. And now he can, for example, see here on the left, kind of the resulting really fine-grained strains and forces that are occurring as, for example, an indenter might kind of poke against the sensor. If you look on the middle part now, you can see kind of a short animation showing these indentation events, where the coloring shows the strains on the surface elements of the SynTouch. Okay, so this is a very accurate, again, finite element simulation of the SynTouch interacting with these indenters. And first of all, me as a computer scientist, I would never have been able to develop something as kind of this whole calibration setup. It's pretty amazing how Yash did that. But I think it's pretty cool that actually he was also then able to show that that the model is actually pretty accurately predicting the forces. So what you can see here on the lower part is, if you look at the lower left, is the following. So he calibrated his finite element method, which means he calibrated, for example, the how deformable the skin is. And he did this by using the data collected with one of the indenters. Okay. And the problem is that you don't have ground truth data for these deformations. So what he did was the following. He took the finite element method to, first of all, predict all the deformations. From those, he then predicted the resulting overall 3D force that would be applied to the biotech, and that he was able to compare to the measured forces through the 6D force torque sensor placed underneath the biotech. And then if you look here on the lower right, he was able to also predict measurements for other kind of indenters with respect to the resulting forces on the force torque sensor, again, placed underneath the biotech. So which means his predictions very well matched the actual measured forces. Okay, so just to repeat what's going on here to make this clear. So what we're using as input is the joint measurements of the ABB UMI. Those give us through then the forward kinematics. We know where the indenter is in the simulated model. We know where the indenter is relative to the biotech. We feed that information into the finite element method to predict how the biotech would deform or react to this indentation process. Through the finite element method, we then also predict the overall resulting force. And that resulting force is then compared to the force that you measured with the force torque sensor. Okay, and he got a very good matching between those. Then with this kind of data, what you can do is you can actually use the electrode measurements, and you train, for example, a point net plus plus structure. And now we can predict, for example, the location of the contact very well. We can predict the 3D force vector. We can train a network to predict that from the electrode measures. But also what I think has never been done before is we can also predict from the electrode measurements the deformation field of the surface of the sensor itself, okay, of the biotech sensor. And the idea is what you can do with these deformation fields is also that hopefully this will lend itself to much better simulations of these contact sensors. The one thing we have not yet been able to reliably do is predict the other way around, where we say, imagine the simulator tells you a certain deformation that you should get based on interacting with objects. And from those simulations, we would like to be able to simulate the resulting electrode measurements that the biotech would give us. If we can do that, then we can train models and controllers purely in simulation and hopefully apply them on the real system. Okay, so this is still ongoing work. In this vein of simulating robots and contacts, we are also looking now at here, this is work led by Carl van Wyk right now, is where we're developing a hand model that also has deformable surfaces. As you can see here on the right, that the surface of the fingertip, for example, kind of deforms in order to make this contact with this, this kind of block that you can see here. Okay, and the idea is that hopefully with such a system, we can investigate, first of all, we get a much better simulation of what happens with deformable manipulation, but hopefully we can also then simulate the deformations and the contact forces and can see what could you do if you had access to this kind of sensor information. Because right now, if we look at the contact sensors that we have, they are still pretty impoverished in the sense of that they are typically mostly on the fingertip, but not on the whole surface of the hand. And in such simulations, we could at least play through these what-if scenarios, right? And here's some work that Yash is doing right now also, where we're trying to see how we can use these kind of finite element method simulations in order to drive controllers to pick up very small objects. For example, now if you look at the middle, this is kind of a deformable sensor gripper hand picking up a very thin washer where the controller is driven by just the overall force measured through this simulated system. On the right, it's even now picking up a very small steel pin, kind of like a needle. And again, the controller is driven by this deformation model. Again, at this point, I don't want to go much more into detail. This is very much ongoing work, but I think it's a very interesting direction so that hopefully we can learn these controllers really through simulation. Okay. If I have time, I can just briefly, do I have 5 more minutes?
Yeah, 5 minutes.
Or, okay, perfect. Great, thank you. Then I just, so far I focused on, let's say, just touch sensing for manipulation, and also kind of using vision, like for visual tracking in order to get training data or detect these objects. I just want to give 2 examples of work that we've been doing on, let's say, mostly vision only manipulation, where one is this work that was published ICCB last year by Arsalan Musavian, where we are learning deep networks that can take an input point cloud and generate, that are trained to generate grasps, 6-degree of freedom grasp for these objects. We can combine this then with an evaluation technique that can actually estimate how good these grasps are that are being sampled, and then also refine these grasps so that they can be executed more robustly. Here you can see some examples. This is a robot picking up some of these objects where, importantly, the system was only trained in simulation. No real data was used for the training, and these objects are not known to the robot, which means these objects were not part of the simulated training data. So this is now really going towards pretty robust 6D pose object grasping in the real world. So this initial work assumed that the objects were kind of individual, but now we're moving towards where the idea is, okay, you have a cluttered scene. You can then use some work that my student Chris Shee did on kind of segmenting individual objects. And then you can use these techniques now to, after segmenting an object, you can generate grasps that are also collision-free, and you can do more sophisticated reasoning. There's a paper coming up that Aditya Murali did as an intern with us that operates more in cluttered scenes for manipulation using these grasp samplers. That's coming up at ICRA. I don't know, yeah, obviously this week. It's, I think, one of the finalists for Best Manipulation Paper Awards, and also Best Student Paper Award. And by the way, Aditya is gonna just joined us as a research scientist also at the Nvidia, the research lab. So this is a very exciting direction. Another thing is I want to highlight actually how good people are at manipulating things without any kind of touch sensing. So here we did build a system called DexPilot that will also be published in ICRA here, is where we're tracking the human hand to remote control the Allegro hand. Let me show you here an example. I hope you can see this in the video, which, I mean, kind of highlights, on the one hand side, first of all, this is a pretty significant system where we use 4 real sense cameras to track the human hand and the articulation. Then that is being mapped over to the Allegro hand. And this is work led by Anko Handa and again, Carl van Wyk. And then a human is actually able to do pretty sophisticated manipulation tasks, right? And this is done without any touch sensing. There's no touch feedback at all. And I hope you can see that a person is actually able to do pretty interesting things here. Here you can see actually, in the interest of time, I'm not going to show this till the end, but here actually they are able to get a, whatever, $10 bill out of that wallet, right? Which I just want to show to highlight that just based on good visual reasoning and understanding that humans are able to do very sophisticated things without touch, but that by no means do I say touch is not important, right? So now let me come to the conclusions. So as I just showed you, I think visual information is, of course, crucial for any kind of pre-touch reasoning and control. I think touch is really important with respect to this kind of just at the last moment, having robustness, any kind of in-hand manipulation capabilities, crucial where you use touch sensing, fine-grained control tasks, also small objects when the visual information isn't there anymore, insertion tasks and things like that. I think touch sensing is going to be really crucial. On our work, we mostly used vision and touch kind of as separate modalities. We did combine them, but not in kind of learning joint embeddings, for example. I think on the one hand side, self-supervised training, as the work that Giovanni hinted at, is a very promising direction because it requires only a minimum amount of supervision. And because of that, you can collect a lot of data in the real world. The problem so far is still that I think the models are not quite as general as some of these physics-based models that you can apply in many different settings, where the self-supervised training so far has been applied in more limited tasks. But I think that is not a fundamental kind of limitations, and I can imagine with more data collection, more substantial experiments that can be expanded. I also showed that I think thorough data collection, where you really put a lot of modeling effort into the data collection process itself, we can then learn more expressive models, which I think then can also lead to good simulation models. And I hope that ultimately we can get to simulation models of context, touch, and deformation that are so accurate that we can actually train both perception, visual perception, and touch feedback in simulation and train policies for these so that they can work in the real world. And I think this would be, of course, a very significant step forward. But there's still quite some work to be done to do this in a very general setting, such that it's also hopefully independent of the sensor itself and applies to different kinds of sensors. But I think in general, we all agree that we still need better touch sensors that also have a much higher coverage, which means so that they cover, for example, the palm and the whole fingers of these objects. And I wasn't able to, unfortunately, see Gordon's talk. I must admit I was still asleep, but I'm pretty sure he talked about some of his really exciting work in providing more coverage for sensing. And with that, I'd like to thank you for your attention.
Thanks, Professor Fox, for sharing. Okay, some quick questions from the audience. One audience asked about what's the performance would deteriorate in data plug if latency was introduced? Have you tested that?
Which question is that? So can you say it again? I was looking at the chat at the same time. I'll just listen to you.
It's a question from Jakub Tomasek. So about the latencies in DexPilot.
Oh,
so
yes.
Do you think that will have lots of
the latency? That's a great question. There is actually a tiny bit of latency from going from the tracking all the way, because we need to track the hands, which has a tiny bit of latency. And then from there, we need to go all the way to the control of the hand. So that is why the demonstration that you saw, they were all kind of sped up a little bit. So we cannot do at this point like really fast finger motion. That is where the latency would be a real problem. So in that sense, we don't need to add artificial latency to make it more difficult. It is already not trivial, but I think it's a very promising direction.
Can I?
Another question from me. So you talk about generalization of the system, like how the vision touch control loop can generalize to different manipulation tasks or to different shapes of the objects. So it's a challenging task, I guess, is for everyone sitting here. But have you thought about if it's hard for generalization, whether it's because we don't have a large enough data set, or the model is not good enough, or simply there's not enough data from the sensor you're using? So how can you get some insight into that?
So I think you mean with respect to self-supervised learning, for example, also, right? I assume. I think one of the problems is really that so far, first of all, I mean, all these different tasks, right, put together, it's just extremely complicated, right? Which means if you really want to have a good coverage, you just need to generate huge amounts of data. And it's not sufficient to just collect, let's say, touch sensor data, but you also want to collect alongside with that the visual data so that you can learn joint controllers that use vision and touch. And covering that space of possible interaction with these objects is just tremendously hard. I think what's, from my perspective, actually very exciting is this recent work that we've seen, especially also in the deep learning vision community, on contrastive learning, where with weak supervision, there has been some really nice progress where people were able to use very minimal amounts of kinds of supervision to learn very powerful feature embeddings for visual data. And I think these kind of techniques, if we can combine them with very, very large scale data sets, I hope that we can hopefully transfer some of these successes to manipulation. So it's on the one hand side, just to get back to your question, I think it's a combination of just the complexity of these problems. I think it's much more complex than recognizing an apple in an image. At the same time, also getting the right kind of supervision for that data is also very, very complex and difficult. And I saw there was one question about a paper. I think I have all the references in the slides, but of course, I can point you at that. Just send me an email.
Hi, Dieter. Hey, thanks for joining us. Hey, and congratulations on the prize.
Oh, thank you.
Your finite element modeling is very cool. Do you know if you're only modeling one particular biotech sensor, or is it applicable across?
That's a great question. And I also see Yash is actually here in the Zoom meeting. So actually, he did it for 3 different biotech sensors. And at this point, sadly, those accurate models do not transfer from one biotech sensor to another one.
I'll just add something here. So
I'll let him chime in.
The element model does transfer from sensor to sensor. The neural network predictions do not transfer that well from sensor to sensor. So the finite element model was tested over the entire data set of different sensors, different indenters, and so on, which, given the generalizability, suggests to me that the mechanical behavior of the sensors is highly repeatable from sensor to sensor. Okay. But because neural network predictions seem to be less predictable, I think that suggests to us that maybe some of the electronics from sensor to sensor may have less repeatability.
Yeah. Okay. So one hope would be if we can train a general model based on, let's say, whatever, 20 of these sensors, then hopefully you could learn a general model, and then for one specific sensor, you just have a reasonably simple additional calibration procedure to refine the model for that specific sensor. So the hope would be clearly that you do not have to go through this calibration process for every single biotech you want to use.
Okay, thank you.
Okay, let's thank Professor Fox for sharing again. So let's welcome our next speaker, Professor Alberto Rodriguez from MIT. So Professor Rodriguez has been working for a long time on autonomous dexterous manipulation, grasping, robot automation, and end-effector design. And today he's going to share some of his work on tactile sensing for in-hand localization, assembly, and manipulation. Let's welcome him.
Thank you. Thanks for the invitation. I'm going to share my slides, and I'm going to need a nod from someone to make sure that you can see them.
Yes, works.
Are we good? Excellent. Nice. So yeah, I think we're running a bit late, so I'm going to try to go as fast as I can through these. But today I wanted to talk about reactive manipulation, and especially the role that tactile feedback plays from my perspective, or can play from my perspective, in enabling reactive manipulation. My interest, or my group's interest in tactile feedback sort of goes back to, goes back to the Amazon Robotics Challenge and sort of the aftermath from that, where we were tasked with building an autonomous system that was capable of picking up a variety of objects in a variety of scenarios, and deal with the challenges that come from occlusions and having just multiple objects dumped in a storage bin. And while many of the teams we develop working solutions, I think that it became clear that many of the things that you would naturally think that a system wouldn't have to do to be able to deal with dense clutter or object variability or constrained spaces, like, I don't know, sort of gently palpating your way towards an object. If you want to grab, let's say, the champagne glass that is in the middle of the bin, or sort of accommodating the fingers on interesting geometric features on the boundary of the object, because maybe you want the fingertip to be on a corner, because that just happens to give you informative information. A lot of those techniques were not, it was impossible to implement them because we didn't have the right tools and we didn't have the right hardware, and we were all basically sort of driven by vision techniques with respect to perception and control. So I sort of became interested in sort of understanding how we could use tactile feedback and how that sort of changes our perspective on how we have to do everything else from perception to planning. This doesn't apply just to warehouse automation, right? So many things that you would think that are interesting from many of these scenarios where robotic manipulation sort of comes as a promise, comes to help us, operating in above, like, or using a tool in a home scenario, or interacting with humans, or ripping things apart if you're disassembling them. It is intuitive that tactile, or at least having a way to master that distal sensing, is important. So I want to talk about that. And to do that, I'll use 3 systems that we've been working on recently: cable manipulation, tabletop manipulation of rigid objects, and insertion. And while I will not describe in depth any of the systems, I want to give a perspective of them from the role that tactile is playing in making this work. So quickly, I think that we all realize that figuring out how to use tactile feedback, it is a difficult question, and in part because tactile feedback comes with many challenges, right? So in a scenario like this, where let's say tactile comes as an image or as some low-level feedback, as in the left, understanding how that sort of plays a role in all the manipulation chain that goes from controlling the interaction between the end effector and the object, or controlling the trajectory of the object, or controlling the trajectory of the arms that are controlling the end effectors. Understanding how that tactile information, which is very local in space and it's very local in time, how that affects upstream all that planning problem. It's quite complicated, and if you're not thoughtful during that planning pipeline, the most likely answer to that question is that actually it's not useful, right? Unless you're careful on how you interact with an object or how you interact with the environment, it is likely that maybe the tactile sensors are placed in the wrong location, or your fingers are touching the object in a way that they don't render useful tactile information. So the question of how do we use tactile feedback, at least in my head, sort of gets transformed to how do we make tactile feedback useful, right? So how do we make sure that everything else we do on perception and on the planning pipeline makes it easier to consume tactile feedback? And along those lines, I want to discuss a couple points that I think that have been quite relevant, or have sort of changed the way that we think about robotic systems. The first one is this idea of targeting contact interactions, which I was mentioning, right? So if you want to use tactile feedback, it comes natural to think that, well, you might want to make sure that you're contacting the objects in those places where the interaction will render useful tactile information. And by useful, that can mean different things depending on the system you're working on. It could be geometric features like in the image above, where you see a corner and that corner automatically gives you some information that can be blended with some vision estimation pipeline. But it could be something else if, for example, the goal is to sort of monitor the stability of a grasp. But the idea is that it has to render useful tactile information. And the second point is that if our system is going to be tasked with consuming that tactile information, because of the timely nature of that information, it has to react fast, which means that you probably want to have a good control over the dynamics of the interaction. In our case, we always like that the interactions we plan for, they define simple mechanical systems or systems with simple dynamics so that we can control them fast enough, which sort of leads to this notion of primitive behaviors that are well understood. Okay, so that's on one side, and then on the right-hand side, so the second thread that I'll mention in the talk is sort of the role that actually tactile plays in the control loop of the behavior of the manipulation system. And this idea of partitioning that role into two key goals. The first one being controlling the contact state. So meaning if the mechanics that you're using to modeling the interaction assume that contacts are sticking, or assume that contacts are sliding, or assume that the grasp is stable, how do we develop a controller that uses tactile feedback that is targeted with ensure that that is happening, that the grasp is stable, that the contact is maintained, that the contact is sliding if it has to slide. And the second control loop is sort of maybe the more standard one, which is controlling the actual state of the object in the environment. So if I have to move an object from here, from there, how does tactile play a role in telling us where the object is in real time so that we can control its state. Okay, so I'll go again over these three systems, but from the perspective of thinking on how do we target these contact interactions, and then how do we partition the role of tactile. And I'll start with cable manipulation because it's the latest one, just in case I run out of time. Okay, so here's a system with two arms, two grippers that is tasked with picking up a deformable cable with relatively unknown dynamics. So the idea is that the cables could have different thicknesses made out of different materials. But the gripper has to pick up the cable and slide its fingers all the way to the end and then insert the end somewhere. And what I want to describe here right now is how we model the process of the gripper sliding its fingers along a cable in a controlled fashion. The basic idea is we have this division of the role of the control system. First, being able to control the state of the object, in this case, the state of the cable, which means for the most part, making sure that the cable stays sort of aligned at the center of the fingers so that it doesn't fall, and that it stays sort of orthogonal to the axis of the fingers. And then the role of the contact state controller in this case would be making sure that the cable can slide nicely when the fingers are trying to slide its fingers. So how do we monitor and control the gripping force between the fingers and the cable so that they can slide nicely? So we don't want the frictional force to be too large because otherwise they would get stuck. And we don't want the frictional force to be too small, otherwise the cable would just fall. And these under very large uncertainty on the material properties of the cables. So we start from this type of feedback that is coming from these sensors, which are probably well known by most people here. A specific instance of gel site or gel slim sensors. It's an optical sensor with a camera inside that just gives us an image of the deformation of the skin of these fingers. So by tracking sort of the image that the camera is capturing, we can estimate the pose of the cable, and we can get an estimate of the distribution of forces when the cable is sliding or it's not sliding. Okay, so once we have that, the idea is that with a simple model of the interaction between the friction and the dynamics between the cable and the fingers, let's say we have a model where the cable is just a particle, a directional particle at the center of the finger, and we want to understand if we're pulling from that particle. This would be sort of the blue diagonal square on top of what it says there, the moving gripper. I don't know if you can see my cursor, but right there.
We can see, yeah.
Yeah, excellent, thank you. If we were to pull in a certain direction from the cable and that location, would that sort of rectangular block, would it move up or would it move down or would it turn? The goal is to make sure that that rectangle sort of is aligned with the finger and it's at the center for as much as possible. So with a simple mechanics model like that, we can learn a linear model where the state is the pose of the cable in the fingers, and the input is the pulling direction. And we gather some data by just pulling from the cables. And then we learn a linear model, which then we can control with an LQR controller, which is feeding sort of the motion of the arm that you saw in the video that is pulling from the cable and is choosing in what direction to pull from. That's what it's necessary to implement the object state controller. We need a model like this, and we need feedback on where the object is, where the cable is in this case. And then on the right-hand side, the contact state controller, which is controlling the gripping force between the gripper and the cable, is tasked with making sure that the gripping force is large enough so that we get a useful tactile imprint to estimate where the object is, right? At the top row, if the gripping force is too small, we get a tactile image that it's not too distinctive. And if instead we apply too much force, like in the bottom row, the frictional interaction, the amount of friction between the finger and the cable is too large, measured right there by the deformation of the gel. So we have a simple PD controller that is modulating the amount of friction, and friction here in between brackets because it's really just amount of deformation of it's an average estimate of the deformation of the gel, which is really controlled, like the shear forces. And once we put together these two controllers, the LQR controlling the robot motion and the PD controller on the gripping force, then is when we get behaviors like this, where the fingers are sliding on the cable and are trying to make sure that the estimation of where the cable is remains in the center. And if necessary, it just regrasps if it detects that it's moving too far from the center, as you can see in the video from the tactile image. Right there, it went too far and it decided to just regrasp. Okay, so the basic idea is leaving aside the details of the mechanics of this primitive behavior, of this sliding behavior, the coupling the controller into these two controllers simplifies the development of the system. And this is a structure that we've been replicating, or we've sort of recreated over the past couple of years in other systems. For example, in a tabletop object manipulation, which is a completely different mechanics, right? So the object is rigid now, and it's two palms instead of a gripper. It has the same kind of sensors now in the form of a palm instead of fingertips, but the same basic idea. And we want to get behavior like this, where there's sort of a sequence of primitive interactions, a pull in this case, now there's a grasp, and we want to be able to execute them on a levering motion in a reactive fashion, so that if we go there and we perturb it, then the system can react in real time. This is the kind of feedback that we get. So geometric feedback on the left and force feedback on the right. We can, if we target the right kind of interactions with the object, like in this case, we can see the edge of the object, we can get useful feedback that then feeds into the, let's say, the estimation of the pose of the object, or on the estimation of whether the object is slipping or not. And the basic idea is that once we get that feedback, with that can sort of populate these two tactile controllers. On the one hand, on the left-hand side, the object state controller, where because we are targeting specific interactions that lead to simple mechanics, in this case, it's just a pulling behavior, but we've sort of replicated this for different primitives, for grasping or levering or pushing. We can replan fast enough that if we maintain an updated estimate of where the object is, we can continuously update that plan that the palm and the arm they have to follow. And on the right hand side, the contact state control, where in this case, sort of the primitive, the pulling behavior assumes that the interaction between the palm and the object have to stick. If the robot detects that the object is slipping, then it can decide to apply more force on the object in this simple pulling behavior. So we're interested in seeing how to generalize that. But here you see sort of the behavior of these two controllers independent from each other, where in the first one, the robot is trying to bring the estimate of the object to the goal. And on the second one, it's just applying more larger or smaller force when it detects that it's slipping. So it's trying to make the contact interaction, it's trying to enforce the expected contact interaction. Okay, so probably the most interesting aspect is this contact state controller. And in general, for the pulling behavior, it's intuitive. In general, what we have is a multi-contact interaction scenario. Let's say in this case, we have two palms manipulating an object that is also in contact with the ground. And there's this notion of grasp stability of the contact configuration. Let's say that if there's a contact on the right-hand side where one of the palms is sliding, there's a slip behavior. We can model the stability of this grasp by sort of making an estimate of the friction cones of each one of the contacts, and then make an estimate of where the actual contact forces are and how far they are from the edges of these friction cones. And then pose an optimization problem that makes an optimal or an informed decision as to what should be the reaction of the palms in terms of reorienting themselves or applying more or less force to sort of improve the stability of that contact configuration. So this means an optimization problem where we're trying to maximize this, what we call the margin of stability, or the margin to the edge of the friction cones, subject to the standard constraints of stable manipulation. So there has to be force equilibrium between the contact forces on the left and the external gravitational wrench on the right, and subject to the contact force constraints. So forces have to be positive, and they have to be inside the friction cones. So we're searching for the reconfiguration of the palms that sort of would maximize this margin of stability. In practice, because we want to be able to consume tactile feedback and we want to be able to react, let's say, to sleep events fast enough, we have to solve this optimization problem very fast, let's say at 100 hertz or 50 hertz, depending on the how fast the system is moving. And the margin is a non-convex cost, and this is also complicated by the fact that the force equilibrium constraint is bilinear, so it depends both on the position of the contacts as well as on the contact forces, and those two things are linearly related to each other in that constraint. So we have to convexify the cost function and linearize around the previous equilibrium to be able to solve this fast enough. So using standard techniques that are used commonly by the locomotion community. But once we have that, then we combine those two controllers, then we can start to generate these regulating behaviors where, let's say that the robot wants to keep an object in a particular location. This is all constrained with one primitive behavior. It's sort of replanning where the trajectory of the object to go to that nominal position, as well as replanning the contact force that it has to exert on the object in real time. You can develop these for different primitive behaviors, and then if we know how to plan through, how to choose which behavior to execute at every time, then we can do these more dexterous manipulation of objects, still within a reactive framework. The problem of sequencing these primitives and choosing sort of the optimal strategy to combine them, that's still an open problem. And in this case, we use a graph-based search to sequence them, but we exploit the fact that we know the geometry of the object. And in general, when we want to execute these for objects with multiple objects or objects with unknown geometry, that's still an open problem. But the point is that, again, the combination of those two controllers generates or enables this reactive behavior. And the last system that I wanted to show, I don't know how much time do I have?
Few minutes.
Few minutes. Okay, so I'll just go quickly. This is sort of using the same strategy, but for a packing or insertion behavior, which has a very different dynamics, right? In part because one of the key issues here is that the interaction with the environment, it's more complicated, and if we want to control sort of the alignment between the object and the whole, the interaction behavior between those two elements is it's not observable to large degree. So it's more difficult to use a model-based approach to guide interaction. So we have to rely on learning policies that are searching for the right kind of tactile interactions that are informative. But the interaction between the gripper and the object, it's still something that we can control, right? So we want to make sure, we want to search for the right alignment between the object and the hole, while making sure that the gripper and the object stay in some stable equilibrium, in some stable grasp. So it's the combination, again, of these two behaviors where there's some learned policy that is trying to do an insertion, while there's some model-based controller that is making sure that the object is not slipping on the fingers, that is getting the job done here. And for controlling the stability of the grasp, we use this notion of incipient slip detection, where by tracking the interaction between the object and the gripper, we can allow the object to receive forces as long as there's no danger of slipping. And when it detects that it's about to slip, sort of the controller doesn't let that happen. So this low-level controller is sitting underneath the exploration policy for learning the packing behavior, which I'll just skip here for the sake of time. But it's basically sort of, this is still ongoing work where we use reinforcement learning to learn to map directly tactile streams of information to an alignment policy. All right, so in summary, how do we use tactile feedback? The key idea is that we should be thinking of how do we make it easier to use tactile feedback? How do we sort of reformulate, especially on the planning pipeline, our thinking so that it is more convenient to use tactile feedback? Key to that is targeting contact interactions that make it easier, and partitioning the role of tactile control into controlling the object state and controlling the contact state. And I just want to thank all the students that did all the work: Francois, Yuan, Yu, Xiaoxing, Niha, and Jose, who have been working very hard to make this happen. Thank you everyone else for listening.
Professor Rodriguez for sharing. Okay, so there's a question from Shan. So in the cable manipulation project, how did you get the ground truth of the cable trajectory?
The ground truth of the cable trajectory in the fingers. So the key idea here is that we don't have to know where the cable, I mean, the dynamics of the cable is very complicated, and it can be modeled if you know enough about the particular cable. But in this case, we don't rely on any estimation of where the cable is, except for the first peak, or how the cable moves outside from the small region that sits in between the fingers. So we know where the cable is when it's in between the fingers. We just use image processing, standard image processing algorithms to sort of make the best fit of the contact patch between the fingers and the cable, and then we just fit an ellipse to that to get the axis of the cable. But outside, wherever the cable is outside the fingers, we don't care to first order. I mean, if you had to do a more complex manipulation with a cable, let's say tying a knot or untangling it, then you do care about with the state of the cable in the general sense. But to generate this sliding behavior, the only thing that we care is where it is in between the fingers. And to estimate it, we just use computer vision techniques to estimate it directly from the image.
I have a question about the tabletop manipulation project. So have you think about you can also use vision for locating the objects and using a force torque sensor at the wrist to measuring the disturbance from the external world? So is there any reasons or advantages of using a tactile sensor instead of vision plus force torque sensors?
Yeah, that is a great question. I think that there is no doubt in my mind, or probably in anyone else's mind, that vision is necessary to solve this problem. And sort of this study was focused on understanding how we can use tactile feedback, but you can't really solve this problem in the general fashion without knowing roughly where the object is initially. So if it's not at the very least to get an initial prior estimate of where the object is, at the very least for that, you need vision. But I think that vision can play a much more important role. And actually our current work, which we're doing right now, is understanding how this fits, or how this sort of synchronizes with the standard techniques now on using affordances to predict where to execute certain behaviors, right? So in this case, this works because we know it's a box, and we can locate the box, and we know how to contact the box. But if you want to do this to objects with general geometry, the right thing to do there is to use vision to guide that decision of where you should contact the object, where you should execute a push or a pull or a grasp. And that decision depends on the overall geometry of the object that can be captured with vision, but it also depends on the local features of the object so that you contact them on places that generate useful tactile feedback. And vision, again, can plays an important role there. So let's say, how do we go from a point cloud representation of the object into understanding where we should sort of contact the object to execute a push or a pull? I think that is a very interesting problem.
Good. Due to the time limit, we need to finish the talk now. So let's thank Professor Rodriguez for sharing again.
Thank you. Thank you, everyone.
Thank you very much.
Okay, now we're done with all the talk today. So let's go to our last part for today's workshop is for panel discussion. So let's welcome all the speakers, or at least the speakers that are available to go back. And we'll welcome Sean back for hosting the discussion.
Okay, thank you everyone for the great talks, and also thanks for all the attendees. Some of you stay up in the midnight, and but I hope everyone has enjoyed the workshop today. We have seen a lot of results for discussions. So at the end, we will have a kind of panel discussion like what we had last year. So last year's panel discussion was very well received. So this year we want to keep this tradition, and we want to encourage some live discussion between the speakers and also the attendees. So before we start the panel discussion, so I can share my screen, and I would like to remind all of us the themes of our workshop. So I think now you can pop your questions in the chat box, so the host organizers can collect the questions from the chat box. Because we were intending to have the generic questions in Slack, but it seems that Slack is quite quiet now because I think everyone is paying attention to the talks, very impressive talks here. So now I think it's time to collect some generic questions to all the speakers. So we have 3 themes for our workshop. The first one is hardware focused. So we have development of tile sensors for perception, action tasks. And the second one, we have multimodal robot perception and action using vision and tactile sensing. The third one, so it's more on human tactile sense, and also how to combine tactile sense with vision. So we have inspirations from how humans integrate visual and tactile information for perception, action, tasks. So today we have seen a lot of talks on these 3 themes. So we have seen these tactile sensors, digits, gel set, tack tape, gel tape. So we have seen these different tactile sensors. And we also see a lot of examples how to use tactile sensors to perform these perception action tasks. So I believe these people who work on the exams will feedback to the people who work on tactile sensors. So any questions in the chat box? Let me have a look.
Okay, so since there's no errors, people are still typing, I would like to ask my first question. So most of you guys have been working in tactile sensing for years, and some of you are working more in the field in recent years. So what's, in your opinion, what are the major differences in the field of using tactile sensing or tactile sensing with vision in the recent years? And what do you foresee for the development of the field in the following several years?
Who would like to go first?
Maybe I can just put forward what I have in my mind. I mean, maybe a very straightforward observation. Neural networks, artificial intelligence seems to conquer all areas, and in robotics as well. And that applies also to force and tactile sensing. So that is definitely a change to a few years back when I started looking into tactile sensing and force sensing. And maybe it's a good thing. So although I have not come to a final conclusion on that for myself, definitely there seems to be a trend to say, okay, we have here a new type of sensor. It can do something clever, but maybe it doesn't give me exactly what I want, or I don't understand really the raw data that comes out of it. So what I do, I take a neural network and it will fix the job. I just go through a very lengthy learning process and then I have fantastic results. So that's my observation.
Maybe I can say a couple of words about this. I think it's a very interesting question. Something that I would like to see in the years to come is maybe a standardization of the field in the same way that if I think about sort of touch sensing, the things that the most close similarity is I guess vision, and in vision we essentially had this cycle, this historical cycle, where at some point CMOS sensors were suddenly very cheap, very available to people, and essentially this enabled really the beginning of a community that would not so much focus on the hardware, but would slowly move more towards service. So essentially building, image processing community, building a computer vision community on top, where you would start building layers and layers of services on top of a reliable hardware. And my hope is that really in the next, 10 years, we can essentially do this jump from having a plethora of tactile sensors that try to do, that maybe use different sensors modalities, but eventually we want to standardize it and we want to start using it, I think, more and more for doing robotics in the real world. I think this would be my hope. So the creation of a field of touch processing.
I think that's a nice hope, but I also think that the situation is much different than for vision, for example. So in vision, we have essentially one data format, essentially, which is an array of pixels with RGB values. But for force sensing, we essentially can have 60 dimensional forces at different locations. We don't necessarily have a 2D array. We might have the sensors distributed on a 3D shape, like the skin from Gordon, for example. And there might be temperature also involved, but not all the hardware will measure all the different modalities. So some only measure normal forces, some can measure shear forces. So it's much more difficult here to unify or find a common data format for this hope, or to fulfill this hope.
Yeah, maybe one quick point on that. It also, yeah, I agree that there's, of course, a much more variety of the kind of sensor types or the data types we're getting. But I'm actually pretty hopeful that deep learning will be able to make really big progress on, let's say, the low-level interpretation of these data types, right? So I think actually that the signals compared to the signals that we have in images are somewhat even more structured, right? If you think about the space of all RGB images versus these kind of sensor tactile feedback, I think that there is with network structures that take advantage, for example, of the 3D nature of that data and the temporal nature of that data, that I think we can make very good progress. The question is, what kind of supervision do we need in order to make that progress, right? And then I think one additional question will be, if we can learn good models, let's say for the reasonably low level sensor interpretation, what comes on top of that, right? Do we, right now also, as we saw, and I agree with Alberto's work, where you then say on top of that, you typically use explicit model-based reasoning to do your controls, but maybe we can even go beyond that then and do more learning also on the higher level control, especially when you want to bring in visual feedback as well.
Yeah, I wanted to maybe contribute another point there. I think that I agree with something that Dieter said during his talk. I think that on the tactile domain, we have, I'm excited by the prospects of what we can inherit or exploit from the development on contrastive learning or representation learning for tactile feedback. I think that learning policies, one of the things that we've seen, I think that lots of people have seen, is that tactile feedback can be difficult to interpret and can be very high dimensional. So learning policies, I think that require extracting more compact and useful representations. And I think that we need development there. But I think that I'm a bit less hopeful on the amount of progress we can get on complete systems because of the tight interdependence that tactile feedback has with hardware, right? So we've seen over the decades lots of development on tactile sensing technologies, and maybe going into actual tactile sensors, and maybe gradually moving into tactile fingers. But I think that we still have a long road to go through to develop tactile hands that have well integrated tactile sensors where the sensors are in the right place and provide the right information for the way we're controlling those hands. I think that until we have a well-integrated piece of hardware that incorporates all of that, it's going to ultimately limit the amount of progress we can make in this field.
Yeah. Sorry.
I mean, to pick up on Roberto's point about, for the field to progress, you need accessible and available tactile sensors for everybody to use. I mean, for a long time, it's basically just a ViTac. You could buy, if you got a large grant where you could buy $10,000 per ViTac. And what's really changed in the last year or two is for optical tactile sensors, the cameras are now available at really small sizes, like a millimeter, a couple of millimeters in size. And that's what has fundamentally driven Roberto's work, also some of our work where we've got a fingertip sized optical tactile sensor as well. And it's because of that hardware availability in combination with the 3D printing, so that people can buy these cameras that are very small, can fit in the size of a fingertip, and then make the physical structure of the tactile sensor themselves. That in principle can open up the field.
Yeah, I would like to follow on this discussion. So we have seen one interesting question in the chat box. So what have panelists heard from people who are not using tactile sensing and doing manipulation. So for example, if we go to SCCV, CVPR, definitely there are people who are working on manipulation without tactile sensing, only with vision. So for these people, why aren't they using tactile sensing? Is that because the tactile sensors are not available to them, or any other reasons? And what we can do to make a greater impact later? Yeah.
Yeah, maybe I can speak a bit to that, because we're doing work exactly in this intersection with manipulation and computer vision. Well, on the one hand side, of course, it is also related to that it's not so easy to get your hands on good tactile sensors these days, right? That are also well integrated. And at the same time, I think it's also just that the pre-tactile phase of manipulation is still such a hard problem from the perception and reasoning side that people feel like they are being kept busy just by that problem, right? Like, how do you pick up an unknown object? How do you move it to a certain location? How do you do things with these objects? So the perception challenges, even without touch, are extremely hard. I hope that over time, as we get, for example, like Roberto's sensors, or also the sensors that Roberto has been developing, as they become more available, hopefully will become also more mainstream, that people, for example, from the computer vision community will start working with them.
So follow-up question to Dieter. So do you think by introducing tactile sensor, it's possible to make the perception problem easier, or it's kind of harder? Like we can probably have more information, but like overall the framework will be more complicated. What do you think?
Well, again, I think until you make contact, as far as I understand it at least, touch sensing doesn't really help you a lot, right? So the huge space of what you do before you even touch that object is still something that you have to solve, right? Like, how do you reason from where to approach an object and all these kind of things. I think touch sensing is clearly going to help in all these kind of tasks. Like, once you make this contact, right, they're going to add robustness. They're going to help, especially with vision doesn't help you anymore when your hand is occluding most of the object, right? If you can't see it, then purely based on vision, you can't do anything with this. This is where touch is going to be really important. Fine-grained tasks, in-hand manipulation. So I think touch is going to be really crucial moving forward. One question is, of course, is it just like learning a joint embedding of vision and touch? Is it sufficient to learn good touch embeddings and vision embeddings and then do some kind of late fusion later on? I think how to combine these in a nice, consistent way is still kind of an open problem at this point.
We have another question, I think mostly for Gordon. The question is, I would like to ask about your insights about large-scale tactile scans. What do you think is the optimal representation of tactile signals, considering the limitation of embedded systems? And for reactive control, considering essentially now the raw tactile data are mostly 2D. There is a very interesting question. And I remember last year we did discuss the types of different tactile sensors and also representing the tactile data in 2D and 3D. Gordon, are you?
Yeah, I'm not sure if I fully understand the question. What we were focusing on is a 3D reconstruction of the surface. And that gives you self-localization of every single point on the contact point. And at the same time, because we are focusing on multimodality, when you know the location of the contact, then you know all the different modality you're making contact with, temperature, vibration, and forces. So I think that was one of the earliest work we ever did that we felt it was very significant. Localization of the actual contact point. And the difficulty with most of the older work is the manual calibration. And if you do large surfaces, it's almost impossible or really, really painful to actually calibrate any of these spatially. And the earlier work of Nemelsky, that was a massive amount of computing that he had to use. He was using massively parallel computing just to actually deal with the robot arm. So that's also one of the issues that we had to solve. That's why we are now pushing towards autonomy. So the tactile system that we have now is just almost plug and play, you know, and you can plug it into any system without adding another computer. And I think that's going to be critical. And I agree with Roberto and all the also Nathan about this. Availability is going to be the biggest contribution to the community to push the whole field forward. We hope we can do that. Caspar asked a very good question earlier today. How much? I think we can hit the target. We will hit the target to get the price down and make it available to everybody.
When will it be available?
You're recording this, so I cannot say. Okay, can I tell you offline?
Okay, yep, sure, please
Thank
do.
you.
So in the previous questions, we have talked a lot on the tactile sensors, the hardware. So the next question is more on the tasks, what we can do with tactile sensors. So it shows the community focus on manipulation tasks or abilities of tactile sensing like precision, dynamic range, while working on tactile perception. I think the main question is what we can do with tactile sensors, like beyond tactile perception.
I think that some of the speakers already sort of hinted at this quite explicitly. There are two aspects of touch that I think are interesting. One aspect is, of course, the perceptual side, determining properties of object, trying to understand the world better. But eventually the part that I think that as a roboticians we care more about is instead closing the loop for control. Being able to use touch for having better grasp, having touch for controlling better in hand manipulation. These are the things that really I think are important beyond just pure perception.
Well, I think there's a grand challenge for the community, for the field, which is basically anything that humans can do, and then to go as far past humans as is possible. You know, our sense of touch is limited. We have long latencies, not necessarily that accurate in some aspects of touch. You know, there's no reason why robot touch can't be far superior to our sense of touch and give far superior manipulation and dexterity in robots than humans can do. When that will happen is another question, but you know, it's an engineering challenge, if you like.
Yeah, totally agree. Yeah. Actually, I would like to hear Wenzhen's idea on this question, because Wenzhen has worked on a lot on the human task. So I would like to hear his idea, what we can do beyond what we have done so far. Wenzhen, are you here? Okay, it seems he lost the connection. And also, there's another question on hardware. So, what are some of the integrated tactile sensors do researchers here use? Only off-the-shelf, the reliable sensor I have found is the single tact sensors from pressure profile. So, to make a greater impact, so can we set up some guidelines? What sensor we can offer?
So I think currently all the labs are still experimenting a lot with different technologies, and we are far away from really commercializing those new technologies. So I'm really curious to see maybe this digit sensor from Facebook to become commercialized. Not only open source, but still a lot of effort to really replicate this stuff. But yeah, that's, I think, still a way to go, as Nathan just said.
Yeah.
Yeah,
yep.
Personally, I would love to see digit commercialized, but well, it's not up to me.
Yeah, I hope we will see this day coming soon. And as we can see for probably for the vision community, so like the RGB cameras are widely used, and it can make the community strive. And if we make the sensors more commercially available and also available to more researchers, so maybe it will help us to make our community strive.
I think an issue with the commercialization is that for it to work, a company has to make money off it. And, you know, all the sensors we're talking about today, I think, for example, Roberto's, Shan's, mine, we've papers on it, we haven't patented it, it's all out there publicly available. So, you know, it's not the kind, it's difficult to get a company to work off the back of that. You need to protect it first. I don't know if anybody else has a comment on that.
But I think having a low-cost sensor available will give the community a huge boost. So think back at the Kinect when it became available, the depth sensing and yeah, whole 3D perception got a real boost, and everything got so much easier than that time. And I think we do need some similar breakthrough through commercialization of a low-cost sensor in the tactile domain as well. I can only encourage Facebook to really push that. I cannot imagine any other reason why Facebook doing tactile research.
Yeah, so Roberto, you heard that you're the richest people here, so we all expect you to ask Facebook to help the community.
I'll do my best. Yeah. But I agree. I think that it would be great to have any low-cost sensor that people can just buy, and and buy tens of them, and if some break, just replace it. I would love that.
Roberto, can you comment on the motivations of Facebook doing this kind of research?
Oh yeah, absolutely. I can make a pitch. So I'm in Facebook AI research. So the motivation for doing generally research in robotics is because we are interested in studying how AI can essentially benefit from embodied intelligence. Arguably the only intelligent system we know are physical systems like humans and animals. So applying AI to robots has a number of challenges, like being able to be robust, being able to really run on on physical hardware, being that efficient, and these are all things for which robotics seems to be a perfect application for developing new algorithms. And touch sensing is because I love touch sensing. I think it's a great thing, and for sort of doing my own research, this was a necessary step.
Thanks.
Yeah, totally makes sense. Yeah, and also like Robert mentioned in his talk, so like OpenAI, they have because they have a lot of great algorithms in in simulations, like reinforcement learning algorithms in simulation. And now they are also moving to this physical hardware, so how to manipulate the cube, and you can see people are paying attention to these physical systems. And I hope this will make our community grow in the coming years. Okay, any other questions?
Well, I'd like to ask Robert, since he has been in this community for very long, you know, what is the most challenging task that we should be focusing in 10 years from now?
Regarding tactile-based manipulation, you mean?
Yep.
So I think all kinds of in-hand manipulation tasks will be quite challenging, where you might need to combine both vision and tactile, of course. That's the basic idea of this workshop. But I think maybe we can even mainly separate these two concerns, because as Dieter said before, vision is mainly for kind of long distance perception, and tactile comes into play if you are in contact with the object. And if you are doing in-hand manipulation like this, then you are already in contact, and you can do that blindly. You don't need really the vision. But yeah, getting the dexterity of the hands, I guess we already have them, and yeah, developing the algorithms to make sense of the sensing and really apply the corresponding motion control signals. That's the challenge for the next years.
Actually, there's a question in the chat box. Actually, I would like to ask before. So the question is, don't we need a task like computer vision had with ImageNet for pushing the fields? So like Nathan mentioned before, maybe if we have a challenge for the fields, it may push the fields grow faster. How do you think? So for example, we have this object set, and we have a common robotic setup, and we have all of the great tactile sensors, what we have heard today, and we set up one challenge.
I think it's much more complicated than in vision, because the standard vision task, of course, is object detection. But what is the standard manipulation task? So manipulation is so much more diverse that it's not easy to come up with some default tasks. I think getting these data sets for tactile perception of different materials is already pushing along that direction in certain fields, of course. And as soon as we see other data sets becoming available for different types of manipulation tasks, we will also see progress there.
Can I comment? Can you hear me? Yep.
Yeah.
Okay. Just wanted to add, and this goes back to the initial point, that before we can have something like that, we need standardization to happen, because what you learn in ImageNet can be reused on any camera roughly, but what you learn from even from two different biotacs cannot be replicated. This is what we heard today, right? So before we can actually get something like an ImageNet for tactile sensing, we need to be able to have standardized sensors or whatever that can be replicated. And calibration, I think, is the key technology for that. To have some mechanism for calibrating sensors so that the data you get out of the calibrated sensor is portable, is comparable across different devices. A bit like what happens with images after you do the calibration. rectification, you kind of have an image that can be reused. And it doesn't matter so much if it is acquired, it's been acquired from one camera or from another.
Kind of hard to define standardized tasks in touch. I mean, I'm sure all of us have had in papers that we pick the task that we like doing, and then the reviewer goes, why didn't you use that benchmark task? And it's like, well, actually, because I thought the task that I thought up was better for the scenario I was doing. And so you kind of need this sweet spot where the task is kind of achievable and doable, but it's also interesting and kind of inspires people, that people actually want to try and do that task themselves. And I don't know, maybe it needs the field to advance a bit more in capabilities first before we start hitting some really interesting tasks that everybody agrees are in, you know, are kind of good to do and interesting as well. I don't know.
Yeah, maybe we can have the community grow for some years, and we standardize these tactile sensors, and then we set up the challenge afterwards.
Once we start getting some tasks that are really human-like in capabilities, but that everybody can do easily with the hardware and the computational capabilities they've got, then, you know, the tasks can get more interesting, and people would maybe want to compare them.
Yeah. Okay, I think it will be pretty much for our workshop. If we don't have any further questions to the panel, so I think we can thank our speakers again. Thank you very much for your great talk. So unfortunately, we can't go to a pub like last year. So sometimes if we go to a pub after workshop, we can all foster better discussions. But we hope we can have such discussions in the pub next year, okay? And also for
thank you also. Thank you very much to the organizers, and in particular to Shan for organizing such a fantastic workshop. Thank you very much.
Thank you.
Thank you. Thank you very much.
Thank you.
Thank you.
Thanks for all the attendees who are from across the world. And on the workshop logistics, so all the so we have recorded the workshop, and we will upload these recordings to our YouTube channel. But we will ask for the permission from our speakers first. So please be patient, and I will send updates by email to your registered emails. And if you have any questions, you can just email me. You have my email in the